Hi there! This is the definition, as you know, of derivative in a single variable with respect to the variable x. But if we have a function of two variables x and y, we can still define the partial derivative done with respect to x by keeping y constant, so we can add the y here, and here y will remain constant while x is varied of h. And we also change notation. Instead of this d, we use a kind of d which I will call dou. It does not have a name, but I call it dou just to differentiate. So dou f in dou x is a partial derivative of f with respect to x, keeping y constant. You can do the same for y. You say y plus h, and here x minus, and you invert y with h basically, and this is a derivative with respect to y, the partial derivative with respect to y. Now we come to a notation, a useful notation. Dou f in dou x, we simply write it fx, so we can easily write the multiple derivatives, for example dou y of dou f in dou x, and it will be written simply as fxy. By the way, a very common notation, which is not as compact as this but more compact than this, is this with dou squared of f divided by dou x and dou y, and of course if it is done with respect to the same variables, so twice with respect to x, we write it with squared x, like in single variable calculus. Sorry, here is an example. We want to list all the derivatives up to the second order of this function f. We can list the first derivatives in the gradient vector and the second derivatives in the Hessian matrix. This is a very useful compact way of listing the derivatives. So let's start to list the first order derivatives with respect to x. It becomes cosine of xy, and with respect to y, this is a constant with respect to y, and it becomes cosine of xy. Now for the Hessian, I don't know, this with respect to x is 2 plus y squared sine, and we have a minus of xy. This with respect to y, it's too small, wait. Yes, cosine of xy plus yx sine of xy with the minus. Now this with respect to x is cosine of xy minus xy sine of xy, and with respect to y it is x squared sine of xy with a minus sign. You see, this matrix is pretty symmetric, which means taking the derivative first with respect to x and then with respect to y is the same as taking the derivative first with respect to y and then with respect to x. Is it always the case? Is the Hessian matrix always symmetrical? Well, if you think about the rules of differentiation, such as how the chain rule and the product rule works, it is pretty intuitive that it must be the case for all the functions, the differentiable functions, of course. But we can prove it directly from the definition of derivative. So derivative is a division of interval. When you take the derivative first with respect to x moving of an interval of h, and then with respect to y with an interval of k, you are doing the difference first with respect to the x direction of f divided by h, and then you do the difference of this derivative with respect to the y direction, and you divide by k. Now in the other way around it would be like this, and if you are here or here, h and k are always the same, so you can take out h from the delta of y because it does not change the interval h along y, and you can write 1 divided by kh of delta y delta x of f. Now if the difference operator is symmetric, you can exchange x and y, and you can then take k inside f because it is constant in all the differences moving by x and moving by y, so it becomes 1 over 8 of delta x delta y of f divided by k. So it is indeed equivalent, exchanging the two derivatives, if the difference operator is symmetric. So the problem is reduced to the symmetry of the difference operator. In fact, the differential operator is essentially a difference operator in disguise. Oh, where? Oh, there. Yes, it's not x. So is the difference operator really symmetrical? We can check very quickly. So we make the difference of the difference first with respect to the first variable here, and with respect to the second variable here. So it is 2, 1, and here it stays 2, and then we make the difference of the difference. So we subtract f. Now we change the second variable to 1 minus f 1 1, and this we give f2 2 plus f11 minus f12 minus f21. You see that if you exchange the 1 and the 2, so if you make the difference first with respect to this, the first, and then with respect to the second variable, it stays the same, because basically you end up with minus f21 and minus f12, and this is the same as this. So yes, the difference operator is symmetrical, and so is the differential operator. You can write it better without the f in a more compact notation. 2 2 minus 1 1 minus 1 2 minus 2 1 minus 1 1, and the other way it would be 2 2 minus 2 1 minus 1 2 minus 1 1. Plus and plus. So you see, it's the same. Now I want to talk a bit about differentials. Now let's say you have a variation in f. You can always write it like this, being fx, the derivative of f with respect to x. Remember, you can always write it like this if you add a small o of x. Now if you have two variables you must add the change in in the y directions. So fy dou delta y small delta plus small o or y. First, if you take the limit, the notation changes and you get df. The small delta becomes a small d by notation. That's a common notation to say you took the limit. So in the limit you can delete the small o and you get this. Now if you divide everything by dt, the differential in t, you can get the derivative of f with respect to t, the total derivative, which means if you have, for example, x which depends on t and y which depends on t, you can get the formula for the total derivative, fx dx on dt plus fy dy on dt. So this is the derivative of the function f of xt yt. If instead of dividing by dt you integrate, you get the formula for the integration in more variables. This is the integral of the f on the x, partial derivative times the x, but the integral df dou f or dou y dy. Now we can give, for example, a geometrical mean to this formula for the total derivative. For example, say you are in a plane xy and you follow a path. In this path, let's say a small portion of the path is ds. Now, ds, the differential, if you replace dt with ds, you can get how the function f changes in your path on the path by ds in the direction of s. So it becomes df on ds equals fx dx on ds plus fy dy on ds. ds is the arc length, s is the arc length, and ds is the differential of the arc length. Now as a quick example, if you want to differentiate a function in a circle parameterized by the angle theta, for example the circle of radius 1, you can write df on the theta equals dou f on dou x dx on the theta plus dou f dou y dy on the theta, and this is fx, we write simply fx. Now dx on the theta is minus sine of theta plus fy cosine of theta. Now let's not fix a path or a circumference, but let's say we are in polar coordinates. We can write x like as r cosine of theta and y equals r sine of theta. So in general, you can take, for example, the partial derivative of x with respect to the polar coordinate theta by doing fx partial derivative of x with respect to theta. Remember, now partial derivative because you have not a defined path, so you have two variables, plus fy dou y on dou theta, and this becomes minus sine of theta minus r sine of theta fx plus r cosine of theta fy. And you can do the same thing for r instead of theta. You put r, and what you get is fx times cosine of theta plus fy sine of theta. And of course you can do this not only in polar coordinates but in general for every coordinates. If you want to change from x, y to x prime, y prime, you you can take the partial derivative of x with respect, for example, to x prime by taking this fx dou x in dou x prime plus fy dou y in dou y prime. This is the particular case of polar coordinates in which you want to take the derivative with respect to r. But in general, it works for any change of variables. Now I want to go a bit more abstract. Now don't think of f of x, y, z, which I've written here, as a function, but think of it as an expression, something you write with x, y, and z. For example, this ellipse or hyperbola, depending on the sign of the parameters. So think of it as an expression. If you have an expression like this equals to a constant, you can, for example, solve it for z and get an expression for z, and you get z as a function of x and y. So an expression like this defines implicitly a function, for example, x in function of y and z, y in function of x and z in function of x and y. For example, here we get two functions, plus 1 over c times this radical, and minus 1 over c times this radical. Now you can't always isolate that. You can't always write it in terms of known functions. For example, if you have a polynomial of degree 5, there is a theorem for which you can't always write z in terms of known functions such as radicals and basic algebraic operations. But you can still invent the name of the function, for example. So not being able to write this to isolate the z does not mean that the function z does not exist. The function z in function of x and y still exists. An expression like this always should define implicitly a function. The square root itself was invented to give a solution, to name a solution for this kind of equation. For example, for the equation x squared equals 2. Now if we don't know, now if radicals don't exist, the square root does not exist, you would say you can't isolate the x. But if you define the square root, then you can write x equals plus or minus square root of 2. So you define two functions as the solution of this. You can do the same a priori with everything, with any expression. You just have to make sure that such a solution exists. For example, for mathematics, the most important part is to prove that such a solution exists, because that is the essential thing. Then how to name the solution is something arbitrary. Now, where do partial derivatives come to play? Let's see. You may not be able to isolate the z, but you may be able to isolate its partial derivatives with respect to x or y, for example. For example, let's try to take the partial derivative with respect to x. Well, we can look for it by taking the partial derivative of f with respect to x. And let's see, because you can write this partial derivative fx as dou f on dou x times dou x on dou x plus dou f on dou y times dou y on dou x plus dou f on dou z times dou z on dou y. Dou x. This is for the rule I showed you before, that by the way is called the chain rule. I forgot to say the name, but it's called the chain rule. Now, the partial derivative of x with respect to x is 1, so here we have only dou f on dou x. Now, what is the partial derivative of y with respect to x? Remember, we are now considering z as a function and x and y as the independent variables. So we are not in this case, but in this case. So being these independent variables, this partial derivative is 0. And we only have these two terms. Now this must be equal to the partial derivative of the constant with respect to x, which is 0. So we get plus dou f on dou z on dou x equals 0. Now we can isolate dou z on dou x, and we get minus dou f on dou x divided by dou f on dou z. So we can isolate always the partial derivative if we have an expression for the partial derivative of f with respect to x and f with respect to z. We can always isolate, in this case, dou z on dou x. So you get this expression for the partial derivatives, this dou z in dou x in dou y, and dou y in dou z, and the inverted thing for the inverted thing. So dou x in dou z, you invert the numerator with the denominator. In fact, notice you have above the derivation with respect to the below variable, and below the derivation with respect to the above variable. So if you have x dou x1 on dou x2, you will have minus dou f on dou x2 divided by dou f on dou x1. Now we did it in 3 variables, but of course it works in any variable. In fact, the only difference is that we will have not only y but a lot of y's, y1, y2, y3, a lot of variables of variables which are independent with respect to x and with respect to each other. So we have this times y1 and dou f on dou y2 times dou y2 divided by partial derivative with x, and so on. All these are multiplied by the partial derivative of one of the independent variables with respect to x times the partial derivative of x. So the only 2 terms which survive are always only the dou x in dou x, which is 1, and the dou z in dou x. So always only these 2 terms survive, and you always get this expression in any dimension. Now this thing of implicit differentiation is a matter which is more delicate than it seems. Now the problems initially are like you are given an expression for a function f of x, and your function f of x is inside an expression big F. So big F is actually an expression, not a function by itself. And you have a lot of independent variables, and your function f is a function of those independent variables. So the partial derivative of f with respect to one of those variables can be written, for example, dou f on dou xi as minus dou big F on dou f, the function this, divided by dou f on dou xi. So in this side you are taking f as a function of f plus the variables of f. So you transformed the expression f in a function, and in this function your initial function is now an independent variable like the others. And this is the case in which you can write this. In the right hand side, f is not an independent variable, otherwise the derivative would be 0. So f has a different role in these sides. That is why this is a delicate matter. You must not confuse the role f plays in these sides. Here it is a variable independent of the others, x. It is a variable of the function f, which is written by defined by your expression, and f, and in the right hand side it is a function and not an independent variable. You basically have to look at this as an expression. This defines your function f with an expression. This equality on the right defines your function f of x implicitly. So this defines big F and this small f. I will repeat it another time because it's important. This is the scheme. You have here f is a function of these variables. This is a function equals this is some expression with these variables and a function f. The function small f here is a function of these variables. So this equality explicitly defines big F, the function of these variables, with the expression on the right. This is an explicit definition. This equality is an implicit definition of small f. So then when you have this clear, when this is clear, you can relate the partial derivative of f with one of its variable, let's say xi, to the partial derivative of big F with some of its with the variable xi. The important is that the variable it's the same, so the partial derivative of f is taken with respect to xi, and so is the partial derivative of big F. Then you can write this expression. This is the relation between these two derivatives with respect to xi. So I hope now this is clear enough. Yes? Well? Oh yes, you're right. I exchanged them by mistake. It's xi and tau f. Now let's go back to integrals. Let's define I of x as an integral in function of x, like this. Then by the fundamental theorem of calculus, remember we have this expression being differentiation, the inverse operation of integration. And if we have here g of x, we would use the chain rule, so it would be f of g of x times g prime of x. Now we are doing calculus in more than one variable. Let's take for example two variables. Then we would have I of x, y. Now let's say we always have from 0 to g of x, but now we have not only a function of t, but also of y. So x is outside the integral, and y is a variable which appears inside the function, inside the integrand. Then the partial derivative, this would be the partial derivative of x of I with respect to x. Instead, the partial derivative of y with respect to y, well, it's simply the integral from 0 to g of x of the partial derivative of f with respect to y in dt, because remember it is a sum, so you take the derivative, the partial derivative of a sum, and you get the sum of the partial derivatives. You can do it because this expression g of x is independent of y, the parameter on which you are differentiating now. So if x and y are functions of s, we can take the total derivative with respect to s. So we have dE and ds, and we sum up these two multiplied by x prime of s and y prime of s. So we would simply have x prime of s times this f of g of x times g prime of x plus y prime of s times this, the integral from 0 to g of x of dou f and dou y in dt. So I hope you have seen how important are partial derivatives for multiple variables calculus. And now that's all, folks. See you next time.